Evening, everyone, and welcome to our Caltech Astronomy Stargazing Lecture for the month of March. I'm Dr. Cameron Hummels. I'm a computational astrophysicist in the department here in Caltech Astronomy. I, as always, will be your host for this evening's event. So thank you all for joining us on your Friday evenings. We have a really exciting program tonight that I'm super excited to present. A quick layout of our schedule of what to expect for this evening. After a couple minutes of announcements by me, I will introduce our speaker for this evening, Dr. Margaret Lazzarini, who will be discussing binary star evolution and how the lives of stars that are orbiting amidst other stars differs from those stars, standalone stars like our own sun, because there's some really dramatic differences in that capacity that she'll talk about. And that should last about 30 minutes. And then following that, we'll immediately jump into a Q&A, not just with our speaker, Dr. Lazzarini, but with an entire Q&A panel consisting of 4 astronomers who each have their PhDs in astronomy and astrophysics and work on different fields of astronomy. So we'll be joined by Dr. Eladia Caiazzo and Dr. Kyle Kramer, who work on different aspects of astronomy, and we'll be fielding questions not just obviously on the content of Dr. Lazzarini's presentation and her talk, but also on really any questions that you may have about astronomy, astrophysics, space science that you've been wondering about. Maybe you've been wondering something for a couple of days, maybe you've been wondering for a couple of years, but hopefully we can shed some light based on our own understanding of the universe and the understanding of physics on questions that you may have. So if you read some sort of newspaper heading recently and you're like, oh, what's that all about? You could ask and we'll do our best. We can't promise to know all the answers, but we can do our best based on our experiences. And that'll take us all the way through about a 2-hour session. So we should finish up at about 9 o'clock this evening. And just as a reminder, these events happen about once a month on Friday nights. Our next one will be a speaker, Dr. Saul Tukolsky, who's a senior professor in the department who works primarily on gravity, general relativity, and gravitational waves like I can't even speak right now, black hole mergers and how they generate gravitational wave signals. He actually wrote the book on numerical recipes and how computational methods work in physics and astronomy. So that'll be super exciting. We also have a sister series of events called Astronomy on Tap. These were traditionally held in a bar prior to COVID, but right now they're still being held over Zoom. I'm hoping to get back to doing these in person in the next couple of months, but until that time, we will be doing these over YouTube or Facebook or Twitter or whatever service that you're watching this right now. And our next one will be a week from this coming Monday on March 14th, Pi Day. And it'll be 2 speakers, one, Max Goldberg, who's going to talk about the role of precision timekeeping and what we can learn about time as well as astronomical objects from just being able to keep time. So things like pulsar timing arrays, being able to detect gravitational waves that we have no ability to detect simply based on the precision information coming from distant timekeeping sources like pulsars. And we'll also hear from Dr. Amy Hoffman, who is a JPL scientist who's going to talk about one of the new NASA missions that's going to Venus in the next few years, Da Vinci Plus, and what we can learn about our nearest neighbor in the solar system, Venus, from these new missions. So I encourage you guys to check that out in just a week and a half. But now for the program of tonight. So Margaret, would you join me? Would you turn on your video and your microphone?
Hi.
How are you?
Fine, thanks. How are you doing?
Excellent. Thank you very much for taking your Friday night to join us. I'm very excited to learn about these massive binary stars and how they evolve differently from our own. So Margaret just joined our department in the last year. She finished her PhD at University of Washington. Was it last spring?
Yeah, June 2021.
Exciting. Well, yeah, thank you for joining us tonight. Do you want to go ahead and share your screen and I'll give a short intro for you?
Sure.
Oh yeah, looks great. Looks great. Okay, so Dr. Margaret Lazzarini is a postdoctoral researcher in observational astrophysics at Caltech. She studies evolved massive binary stars using observations from multiple space-based telescopes. She was a high school teacher before getting her PhD in astronomy and is very passionate about STEM education. She enjoys swimming, being outside, and spending time with her family, especially her adorable dog, Melba. I look forward to having the opportunity to meet Melba at some point soon. What breed of dog is Melba?
She's a mini golden doodle. She basically looks like a live action teddy bear.
That's great, but she's not with you now. She's not going to like come in the back of the.
No, she's not in the room, just in case she barked at something during the talk.
Excellent. Okay, well, I'll let you take it from there, but thank you for joining us.
All right, thank you. All right, so I'm going to get started. Thanks again, Cameron, for the great introduction. So I'm going to be talking today about massive binary stars in Technicolor. And so to get us started, I'm going to start at square one. I'm talking about stars today, so I want to kind of just explain what a star is. So a star is a sphere of plasma, and it is held together by its own gravity and powered by nuclear fusion and its core. And so plasma is one of the states of matter besides solid, liquid, and gas. And basically, for something to be a plasma, it has to be really very hot. And that heat kind of comes from this nuclear fusion in the core of a star. So the way that stars kind of hold up their shape, there's this spherical shape. And as I mentioned, they're held up by their own gravity. And they are kind of in this spherical shape balanced between the input of the gravity, which is kind of crushing in towards the center of the star, and this outward force of radiation pressure, which is basically like the force of the heat from that nuclear fusion in the core of the star kind of pushing out. And these two forces balance to kind of form this spherical shape, and kind of, perhaps changes in how this balance happens is going to kind of dictate different changes that might happen to a star over the course of its life. And when I'm talking about the gravity of a star, the gravity is really dictated by the mass of a star. So the more mass something has, the stronger its gravitational field will be. And so more massive stars, you can imagine, have kind of a stronger force crushing in. So they must have kind of a stronger force of this radiation pressure pushing back out. And if something has less mass, it's going to have slightly less force kind of crushing in and a little bit less force necessary to push back out. So a star's mass will kind of dictate its gravity, and that essentially means that the star's mass is going to kind of dictate its evolution in a lot of ways. So this is like an analogy I've heard before that I find very helpful, is to kind of compare stars. So low mass stars versus high mass stars are kind of like thinking about low mass stars as a Prius and high mass stars as a Hummer. So low mass stars have a relatively small fuel tank, which is basically like all of the mass in the star that it has to do nuclear fusion with. They live for a very long time. They're a bit cooler, a bit fainter, and they burn through their fuel very efficiently. So that's kind of why they live for a long time, even though they have kind of a small fuel tank. High mass stars are kind of more like Hummers. So they are really big. They have a lot of fuel in the tank, but they kind of live fast, die young. They burn really hot, they burn really bright, and then because of all that, they burn through their fuel very quickly. So I'm going to next talk a little bit about kind of the general evolution for a low mass star. And I want to emphasize at the bottom of the slide here, this is simplified and not to scale at all, but just kind of showing the general overview of what happens in the life of a low mass star. So we kind of define this boundary line for low mass stars versus high mass stars as roughly 8 times the mass of our sun. And our sun is a low mass star itself. And so these low mass stars will start off their life on what we call the main sequence. And you can think of that as basically this star, it was born, it's kind of gearing up, and then it turns 18. It's, a fresh adult. It's doing its thing. What it's really doing is it's fusing hydrogen to helium in the core of the star. And that's kind of what it's burning in the, main adult phase of its life. There comes a time where it starts to run out of that fuel in the core. The core will kind of contract a little bit, which causes the outer layers of the star to expand a little bit, which turns it into a red giant. And the reason that it goes from being kind of yellow, like our sun is a yellow star, to red, is that when it kind of expands a little bit, it kind of cools off, and that makes it look a little bit redder. And then for low mass stars, essentially, remember that it has this balance of the gravity in and this radiation pressure out. And because low mass stars don't have quite as strong of a gravity pushing in, it's hard to get it essentially hot enough in the core of that star to kind of go further in different stages of fusion in the core of the star. So it basically runs out of the hydrogen, it starts trying to fuse helium, and then it kind of runs out of gas. And essentially at this point, the star kind of stops fusion in the core. It goes from a red giant. It essentially you can imagine this radiation pressure in the core of the star just kind of turns off. So you then have kind of this inward crush from gravity. You don't really have something kind of counteracting it. So what happens is the interior of the star collapses down, and the exterior kind of outermost layers of the star kind of puff off to form this thing that we call a planetary nebula. So that's kind of this colorful, it's kind of, if you want to Google some beautiful astronomical objects, planetary nebulae, I think, are some of the most beautiful, but it kind of puffs out these outer layers, and you're left with this really dense kind of leftover from the center, from the core of that star, which we refer to as a white dwarf. So a white dwarf is kind of like the corpse, essentially, that's left over after a low mass star goes through all of its phases. So high mass stars have a kind of analogous but slightly different process. So they also start on the main sequence. They're hotter. So this star I'm showing it as blue. Basically, bluer things are hotter. If you imagine if you've ever looked at the flame of a candle, the hottest part at the bottom is kind of blue, and then it's cooler up at the top where it's yellow and red. So high mass stars start off on the main sequence as well. And then this is kind of very simplified, but basically they finish fusing hydrogen into helium in the core. And then they kind of they become a supergiant kind of in the same way. The outer layers puff up and the central core kind of condenses a bit to do kind of next level processes in the fusion. Because the gravity pushing in is stronger for high mass stars, they can actually get hot enough to do kind of more advanced types of fusion. And basically you get to this point in a high mass star where the core of the star is made up of iron. And because of, just kind of atomic physics, it's not that favorable to try to fuse iron into a heavier element. So essentially you reach this point where fusion just kind of stops in the core of this high mass star. And because there's so much mass and gravity is crushing in so much, it essentially stops this fusion. You have an explosion as kind of the core collapses and the outer layers kind of crush in. This explosion is called a supernova. And then depending on the mass of the star, it will either turn into a neutron star. So it's basically the material from the star crushes in until it's kind of a ball of subatomic particles called neutrons that essentially once they reach that point, these subatomic particles will kind of push back on each other and kind of maintain this neutron star. If the star is really massive, it will collapse down into a black hole, which means that even these subatomic particles are not strong enough to prevent the total collapse of this star. And we're left with a black hole, which is infinitesimally small point in space that contains all of this mass from the high mass star. And as indicated by the title of my talk, I'm going to be focusing on high mass stars, partly just because I think they're really cool. They're the ones that, die in these massive explosions, and then they also turn into these really exotic objects, neutron stars and black holes. One other thing that's interesting about high mass stars is that most massive stars are not just kind of single stars. They form in binary or sometimes even triple or even quadruple star systems. So if you have kind of a group of these high mass stars, a large fraction of them are actually going to have a companion star, or maybe even two companion stars. And one thing that's also very fascinating is that a large fraction of those binaries are actually close enough to interact. And that means that, these two stars are not kind of doing their thing completely isolated. They have another star that's kind of nearby that they might kind of, come in might interact with at some point during their lives. So kind of thinking back to my first slide, when we're talking about a high mass star, we're often talking about a high mass star with a friend. So they seem to be very happy about this. When you have these two stars that form this binary system, they are actually going to be orbiting around each other. So what they're kind of essentially doing is they're orbiting, kind of moving like this, and they're going to orbit around the center of mass of the system. And one way I like to think about that is if you took these two stars and you put one star on either end of a seesaw, and you could perhaps like move the central point, I think it's called a fulcrum, where that seesaw tips back and forth, and you figure out like the exact balancing point for where these two stars would balance out. That's kind of the point in space where these two stars would orbit around. Okay, so bringing us back, okay, we're interested in evolution. We're talking about high mass stars. So we're going to kind of move from this simplistic picture of high mass stellar evolution. And yeah, we've got two stars. We're going to say, all right, we have star one, it's doing its thing, main sequence, supergiant, supernova, turns into a black hole or neutron star. We have star two that's going to be kind of following a similar track. Keep in mind, as I mentioned, that the mass of the star will kind of influence the way that it evolves. And what that essentially, higher mass stars will live faster, die younger than lower mass stars. So, both of these stars don't necessarily have the same mass. It's kind of a roll of the dice in some ways, exactly what the mass of these stars are. So it's a bit improbable that they would have exactly the same mass. So they probably wouldn't be going through these steps at exactly the same time. But we still, could say we kind of understand this general picture. But wait, right? One thing to call your attention back to that I mentioned is that a large fraction of these massive stars in binaries are close enough to interact. And so what do I mean when I say that these stars might interact? So let's, focus in here on one of these massive stellar binaries. One thing that they could do that's considered interacting is that they can exchange mass. And so when they exchange mass, you have one star could be kind of, this star could be losing material that could be flowing onto this other star in the system. And you might be thinking to yourselves, right, as I mentioned, the mass of the star really matters for kind of how these stars evolve, how quickly they evolve. So if we can exchange mass between these two stars, we're like changing the equation as it's being calculated, right? We know that like it might have started off its evolutionary process with one mass and now it's changing. That could kind of throw some complications in things. One other way they can interact is through a stellar merger. And so as it sounds, these two stars can literally merge together to form one star, which is kind of crazy. So you could imagine, right, that in kind of a similar way, this new star that formed after the merger now has a lot of mass. And also you can imagine that the inside of that star has been kind of like mixed up somehow during that merger process. So that could be interesting and weird for the evolution of these stars. And there's like one other kind of interesting phase I want to highlight, which is called the common envelope phase. And so let's take, we're looking at these two stars. Let's take a little X-ray view inside of the star on the right here. And so the star has the core, and then this outer kind of layer is called, we refer to as the envelope of the star. And so in a common envelope, one star can enter into the envelope of the other star, and this star will be kind of like orbiting around inside of the envelope. It basically can have, so what happens is like it's orbiting inside this envelope, and then there's friction between this star and the envelope of its companion. So you can either, common envelopes can result in stellar mergers. You could end up kind of puffing out this envelope and being left with these, like the naked core of this star and the other one. So it's interesting and it's complicated. So we know that this is not what happens when we have two stars, two massive stars in a binary system. They are not just kind of, neatly doing their own thing. It's a little bit more complicated. So binary stellar evolution is complex. So I'm showing here a cartoon, which is showing one possible life cycle for a massive stellar binary. And I want to emphasize that this is one possible life cycle. So there's stars that could go through only some of these phases. Maybe it's the stars might merge kind of earlier on in this process. There's some that might kind of go through some of these steps in a slightly different order, or might go through some of the steps more than once. So this is just kind of a snapshot to kind of highlight what some of the most interesting phases may be. So we have our two massive stars at what's called the zero age main sequence. And so zero age is like the 18th birthday, right? So the main sequence is adulthood for stars. Zero age is like the very beginning of that adulthood. Then they could go into this mass exchange phase that we call Roche lobe overflow. You could have a situation here where you have a helium star, which is basically that where the outer layers of the star got stripped off and you're kind of left looking at like the core of the star. And then you could have that in a binary with a main sequence, just kind of like a regular adult star, but you can see it maybe gained a little bit of mass. You could have one of the stars supernova. So again, if they're not going to likely have exactly the same mass, so they would undergo supernovas at different times. So you'll have one star supernova, the other one is still a regular star. And then you're left with a neutron star, which I'm showing here with some jets kind of pushing out of here, indicating maybe it's a pulsar, which is like a rapidly rotating, highly magnetized neutron star. So you can have this situation. You can have a phase called the high mass X-ray binary phase then, where you have the neutron star is now accreting material or like pulling material from the massive companion star. We have this common envelope phase I mentioned. You could have, again, you can have some of these like a stripped star in a binary with a neutron star or a black hole. You can have Roche lobe overflow. You can have a second supernova. Then you can end up having two neutron stars that are in a binary with each other, which could eventually result in a binary neutron star merger. And then eventually you could form a black hole. So there's a lot going on here, and kind of, part of what I'm trying to illustrate by kind of walking through this is that this is complicated and it's interesting. And there's still a lot that we're trying to kind of figure out about some of these more difficult to model stages, which is what I think is so interesting and exciting about this field. And a lot of the interest in studying binary stellar evolution in recent years has been fueled by this kind of last two panels of the picture here, where we have this binary neutron star merger, which forms a black hole. So when compact objects merge, they produce gravitational waves, which you might have heard about in another stargazing lecture. There's a lot of people at Caltech who work really directly on gravitational waves. I don't personally work on them, but they're kind of, an interesting, motivation for the type of work that I do. So a compact object merger could be, so neutron stars and black holes are compact objects. So you could have a neutron star and a neutron star merge. You could have a black hole and a black hole merge, a black hole and a neutron star merge. And when this merger happens, they produce these things called gravitational waves. And then they form, after they merge, they're going to form a black hole. And so to give a picture of what gravitational waves are, I have a little animation here showing two neutron stars. So gravitational waves are ripples in the fabric of space-time. And basically what happens is when you have two really massive things, like compact massive things, and they kind of move around, you can imagine it's like if you could take the 3 dimensions of space-time and flatten them out into a flat surface, like a stretched out sheet, like you can imagine here, or the surface of a body of water, like a pond. And then you have two things kind of moving around, kind of changing their orbit. You're going to get these ripples that go out, which you can see kind of animated here. And so we can detect these ripples as kind of changes in like the dimensions that we can measure in space-time. And that is what gravitational waves are. We've only been able to detect gravitational waves since 2015, I think was the first time we detected them. And so neutron star and black hole mergers have been detected with gravitational waves. And here's a figure showing the masses in solar masses of all of these mergers that we've observed. There's kind of a lot going on this plot here, but what I want to kind of emphasize here is that there's a lot of mergers here. We have kind of a fairly wide range of masses. All of the points in turquoise and orange are black hole and neutron stars that we've detected with gravitational waves. So you'll see these, like this one here, you have a point and another point and then an arrow to a third point. So that means you had a black hole of this mass and a black hole of this mass that merged to form a black hole of that third point's mass. On this same figure, we also have black holes that we detected with light or electromagnetic radiation. And these are black holes and neutron stars in binaries with generally other stars. And so in the magenta here, we have black holes, and in the lighter yellow here, we have neutron stars. And so one thing that has been really exciting and interesting since we've started detecting all of these black hole and neutron star mergers with gravitational waves is this kind of fundamental scientific question, which is how do these compact binary systems that merge to produce gravitational waves actually form? And, you know, I think like the very first, some of the gravitational wave events that we've detected with merging black holes, we don't quite understand how you would get black holes that big if we're just kind of forming them through the regular ways that we understand how stellar mass black holes form, which is kind of that picture I painted at the very beginning of the talk, where you have a high mass star that evolves, goes supernova, and then turns into a black hole. So it's kind of gotten the community really excited, and there's a lot of ideas, and we think now that it's kind of a combination of multiple different paths to form these types of systems. So there's binary stellar evolution, which is what I'm talking about today. And then there's other stuff like dynamical evolution in dense environments, where maybe instead of having these two black holes form kind of through this binary evolution process, maybe they formed separately and then came together. There's some ideas of chemically homogeneous evolution, which is basically this idea that the stars are spinning so rapidly that the inside of the star is like churning up, which changes the way that they evolve. And there's others. There's kind of some other ideas that I, just kind of highlighting some of them here. Okay, so I'm focusing on binary stellar evolution, and that's what I kind of focus on in my research. But it's kind of this big idea that in order to kind of understand how each of these different pieces contributes to this whole population that we're observing, we need to kind of deepen our understanding of each individual pathway kind of independently so that we can kind of put the whole picture together. So bringing us back here to our picture of binary stellar evolution, there's a lot of ways that people go about kind of trying to understand this process more deeply. Some people study these gravitational wave events that come from these last couple stages. There's a lot of people who are studying, binary stars kind of while they're still in their main sequence phases. And the phase that I focus on in my research is the high mass X-ray binary phase, which is this phase here. Where, if you recall, the primary star has already undergone a supernova. So primary is just the more massive one to begin with. So the more massive star has become a supernova, and the other one is still like a massive star. And so high mass X-ray binaries, this is to switch to an artist's depiction of a high mass X-ray binary. They are systems in which a black hole or neutron star, which again we refer to as a compact object, accretes mass from a high mass companion star. And we observe these things using light. And so I'm showing here kind of an overview of the electromagnetic spectrum and showing kind of this idea that different types of light have different amounts of energy, and that's going to kind of influence where they are produced in the universe. So light waves like radio and infrared are lower energy, and then things like ultraviolet, X-rays, gamma rays have higher energy. And so like essentially the hotter something is, the higher energy radiation it's going to produce, is kind of a rough rule of thumb to understand how we go about studying these. So when we're trying to study the black hole or neutron star in these high mass X-ray binaries, we study them using X-ray emission that comes from the accretion disk around the black hole or neutron star, which you can see kind of in the background here in this image. These accretion disks is basically it's the inflow of this matter from the companion star onto the black hole or neutron star. It gets really, really hot, and that's why it emits a lot of X-ray light. And they're super bright, which is really helpful for us observationally because it helps us find them in space. And we have to observe these things with space-based telescopes. X-ray telescopes are all in space. And so like, for example, Chandra X-ray Observatory and NuSTAR are two of the ones that I've used in my research to study these. And then to get a full picture of this system, we have to also look at infrared, optical, and ultraviolet light, which are lower energy light that we see coming from this high mass companion star. And again, so high mass companion stars are hot, but they're not as hot as the accretion disks around black holes. So they're not going to be creating quite as energetic electromagnetic radiation. But we use this light to identify the companion star in these systems and to study it further. And also we can kind of understand the galaxy and the stars that hosts this X-ray binary system and the stars around it. And we can do these observations with both ground and space-based telescopes. So I'm going to bring it back for a second just to the title of my talk. So I'm talking about massive binary stars in Technicolor. And Technicolor is like a term from kind of the movie making business, which is this process of color cinematography where you use synchronized monochrome films. These are like films in one color, and you kind of synchronize them all together to produce a movie in color. And so that's kind of what I'm doing when we're talking about studying these high mass X-ray binaries. Is we're using this X-ray emission where we can only really look at the black hole or neutron star, and we kind of combine it with this infrared, optical, and UV emission where we can only really see this high mass companion star. But when we kind of, synchronize these two things together, we can get a full kind of Technicolor picture for what these systems really look like and kind of how they behave. Okay, let me just check on my time. Okay, so how do we actually find and characterize these high mass X-ray binaries? So a lot of the work that goes into studying these high mass X-ray binaries focuses on local group galaxies. And so these are basically just galaxies that are really close to our own galaxy, the Milky Way. So here's the Milky Way. It has these small satellite galaxies that orbit around it. And then there's two other big galaxies in the local group, the Andromeda galaxy, M31, and the Triangulum galaxy, M33. There are also a lot of people who study high mass X-ray binaries in more distant galaxies where you kind of get like the combined light from all of these multiple systems. But in my research, I focus on studying them in the local group. And so to study these in local group galaxies, I'm going to focus really on Andromeda M31, which is our next door neighbor galaxy. We can combine these X-ray observations with UV, optical, and infrared observations. And so I'm showing here a movie showing an image of Andromeda M31 taken with a ground-based telescope. And I'm going to show what we can do when we use space-based telescope images of Andromeda taken with the Hubble Space Telescope, which is a lot of the optical UV and infrared data that I use in my research. So you can see we're kind of zooming in on this ground-based image, and then we switch to this image taken with the Hubble Space Telescope. It's actually a little grainy, but I think that's more the resolution of the image or of this video than the resolution of the actual image. But as you zoom in, you can see every tiny little speck of light we see in this image is an individual star in this galaxy that is far away. And so what we were able to do, so this image is taken from a survey that was able to look at kind of part of the disk of M31, which I'm going to switch to on the next picture. So this is the combined image that we were zooming into in that video, taken with the Hubble Space Telescope. And we were able to look at the at M31 Andromeda here and individually identify, I think, 22 million individual stars in that galaxy, which is really like tens of millions of stars in another galaxy, which is really crazy. So we combine this, again, we're using this optical light imaging to study these companion stars, but we need to also be able to identify the X-ray emission from these black holes and neutron stars. So to do that, we use overlapping images taken with the Chandra X-ray Observatory. And so this is a 3-color image, like, mock-up of what this X-ray telescope image looks like. X-rays, obviously, we can't actually see with our eyes. So we have to kind of like translate the energies of those X-ray light photons into what we would imagine they would look like if we could see at that energy range. X-ray images are never quite as fun to look at as optical light images, but I'll kind of zoom in here so you can see that we have these kind of bright points here, and these are all kind of emission that is coming from some really hot thing that is in this galaxy. So it can be like a black hole or neutron star in a high mass X-ray binary, but you can also see this type of X-ray emission from other objects as well. So again, to kind of remember, so we're looking at the combined image here from Andromeda and an image of Andromeda from the Hubble Space Telescope with this X-ray image from Chandra. And we can say, all right, let's look at kind of one of these black holes or neutron stars that we've identified in our Chandra imaging. And I want to see, what does it also look like in the Hubble Space Telescope imaging? So I'm showing you here one of our examples. On the right is this X-ray image from Andromeda of this region of Andromeda that's about a 400 times zoom in from the previous image I showed you. And X-ray images, again, super pixelated. They're not that great to look at, but we can, study the photons and understand the energies of them, and we can characterize and understand what these things are. So this is basically like a long phone number that identifies this source. It's actually its position on the sky. So we see the circle here marking the position of this X-ray emission that we've detected from a black hole or neutron star. And then in here, we see this really zoomed in image from the Hubble Space Telescope, where we can actually see this really bright blue star here. That is the companion star in this high mass X-ray binary system. Okay, so we find them, but now what, right? We actually want to understand them. So some of the things that we want to find out are things like, what is this companion star like, right? So what's its mass? How hot is it? How big is it? And we want to know, is the compact object a black hole or a neutron star? We want to know how old is the system? And all of these are kind of things that would help us if we wanted to draw like a cartoon style picture of the evolution of this binary system. We need to know some of these details. And these types of observations, these things that we can measure using our X-ray and optical observations, are things that we actually use to improve our theoretical models that we use to predict things like the merger rates of compact objects that we would be able to detect with gravitational waves. So the last thing I kind of want to highlight is a third X-ray telescope, or a second X-ray telescope, a third space telescope that we can use here. This is an image of M31 taken with NuSTAR, which is a high energy X-ray telescope that is essentially showing us kind of like even higher energy X-ray emission from this accretion disk around the black holes and neutron stars, which allows us to kind of even further characterize the accreting compact objects. Okay, so wrapping up, our takeaway points here. Hopefully I've maybe convinced you that massive stars are really interesting. We know that most of them are in binary systems. Binary stellar evolution is super complicated and thus very interesting. And that some of these massive binary stars that are in these systems form binary black hole or neutron star mergers that we can detect with gravitational waves. And the last thing is, observing these high mass X-ray binaries can help deepen our understanding of this massive binary stellar evolution process. So I am going to pause here and say thank you, and I'll take questions with the panel. Thank you so much.
Thank you very much, Margaret. That was excellent. Yeah, I liked your comparison of the Humvee for the high mass star that eats up all of its fuel very quickly versus the Prius for the low mass star. I think that's a very apt analogy. So
thanks.
Okay, so audience members, oh, I'm being too loud. It's setting off my clapper that turns on the lights in here. So audience members, I encourage you to ask your questions. You can ask them in the YouTube comment section or the Facebook comments, but what's probably easier is, and I posted the links in those comment sections, is to go to an external website. It's totally free. You don't have to register so you don't have to get your email. You're not going to get spam. It's just a website where you can post your comments, but the benefit is that it upvotes. You can upvote other people's comments and questions so that we get kind of a prioritized, what are the best questions to ask our panelists first. And the link, let's see, the link that you can go to, as I said, I posted it there, but let me just very quickly share my screen so that you guys can all see it. And that is here. So if you go to menti.com and type in this code 93342651, it'll bring up this menti.com interface where you can type in your question, and it allows you to upvote other questions that other people have asked, and we'll go through and preferentially ask the ones that are most highly upvoted. But for now, we will immediately go into our Q&A panel consisting of Dr. Lazzarini, who just spoke, myself, Dr. Cameron Hummels, and two other members, Kyle and Ilaria. Do you want to jump in here? I'm going to stop sharing this. Hi, guys.
Hello.
Welcome. Thank you for joining us tonight. I guess I'll have each one of you give a short, minute-long introduction on the science that you work on, so our audience knows, obviously they can ask whatever questions that they want, but they might be able to better key it in based on the specialties and the areas of research in which we actually work. So, Ilaria, do you want to go first?
Sure. Hello, everyone. I'm a postdoc at Caltech. I've been for 2.5 years now. I work on lots of different things. I'm very interested in, the last stages of stellar evolution that Margaret covered somewhat. I worked on neutron stars, and actually I've been working a lot at the endpoint of low mass stars, so white dwarfs.
Great. Thanks, Ilaria. And Kyle?
Hi, everybody. I'm Kyle. So I've been at Caltech for about 1.5 years now. So Margaret mentioned very briefly sort of another way you might form black hole binaries, which is in dense environments. So these dense environments are what I study. So dense star clusters where many stars are packed together very closely and where they can interact in even perhaps additional surprising ways beyond some of the things that Margaret talked about. So.
Great. Yeah, I'm Dr. Cameron Hummels. I am a researcher who works on computational modeling of galaxies and how they form and how they evolve over really, really long timescales. Because when you think of a galaxy, like at the end of Margaret's presentation, she was talking about our nearest massive neighbor, the Andromeda galaxy, which many of you may have seen. You can actually, in dark enough skies, you can see it with your naked eye, but it's usually better to look through binoculars or a telescope. But that system, like many galaxies, it takes a very, very long time to actually change, like millions or hundreds of millions of years. And so we can't necessarily learn how these systems are changing over long periods when we've only really known about them for 100 or so years. And if you compare an image of the Andromeda galaxy, for instance, and compare that image that was taken today or tonight with one that was taken 100 years ago, there's very little change because it's like the blink of an eye for a system like that. So I run computer simulations where we can artificially accelerate time in the supercomputer that allows us to follow how these things evolve over billions of years and see how they form and how they change over time. So anyway, yeah, I encourage you guys again to check out the link that I had posted in the various chats. I see many of you have already posted your questions, and furthermore to upvote the ones that you think are the most compelling. So we're getting a good cross section of questions that people have asked. So let's see, the most highly voted question here thus far is, how long does it take a normal star, a normal sized star like Earth's sun, to go from its original size to a red giant? And then how fast does a supernova happen I guess that's kind of a separate question. How fast then, after it turns into a supernova, does it take to actually explode? So I guess this is a question that's relevant to actually all of us in some capacity. So anybody who wants to chime in first on this, but by all means.
I can start. So as Margaret told us at the very beginning of our talk, the time really depends on the mass. So if you're really talking about our sun, that takes quite a long time, about 10 billion years. And so we are about halfway through the adult life of the sun, as Margaret put it. And our sun will not go supernova. And also because the mass is not high enough. So really the mass is what determines everything about the life of a star. And the other thing is if it's in a binary or not, I guess. Those are the two main things that determine the entire life of a star. So for the sun, it won't go supernova. And it will last about 10 billion years. And then if you go to higher and higher mass, the adult life lasts less and less and less, and the order of even of millions of years. But maybe, Margaret, you want to add something?
I think you covered it. That sounds good.
Wait, so I missed it. I was too busy worrying about the other questions. Did you cover the duration of the actual supernova? Like how quickly that occurs?
I did not.
Oh, okay. I actually don't, like once the implosion, I guess, once the fuel mechanism well, I guess it depends on the type of supernova, but let's just talk about the most common supernova type 2 supernovae, which are generally from these massive stars, the ones that form from structures like what Margaret was talking about. So these stars, they have their nuclear fusion going on in the center, and as was just discussed, they build up heavier and heavier elements there that are providing pressure to support all of the overlying layers that are trying to force their way to the center because of gravity, and eventually that fuel runs out. It no longer can produce sufficient energy to prop up those layers that want to collapse down, and then it just starts free falling down towards the center. So I guess the time scale for that is the crossing time of the system, usually the size of a massive star. Do you guys, size of a massive star at late time evolution is an AU, all right? Something like I guess for reference, I'm using jargon, an astronomical unit, which is roughly the distance from the center of the sun to the Earth's orbit, on par with that scale, not necessarily exactly that, but I feel like that's a typical scale for like a massive star late in its evolution. And what is that in terms of light time? That's like 10 light minutes. So nominally it would just free fall at 10 minutes. It wouldn't take 10 minutes. It's not traveling at the speed of light. What is the gravitational free fall time for something that's an AU size thing? I'd say on the order of a day, something like that. I don't know. Correct me if you, Kyle, or Margaret or Ilaria, if you know. I'm just kind of hand waving here, but I'd say rough time scales like a day. But then once everything gets super dense in the core of the, so it's going to collapse. It's going to collapse until it gets really dense, and that's when bad things happen, because you get nuclei that are forced so closely together that the strong nuclear force takes over, and then it flings them outward. And that part happens on like second time scales, very quickly, and then it explodes outward at very high velocities, sometimes approaching some reasonable fraction of the speed of light. And then, I mean, I guess it's hard to say when the supernova ends, right? Because it's expanding outward, it's shining very brightly because it's very hot, it's traveling very quickly outward. I mean, you can look up in the sky with your telescope and see objects like something called the Crab Nebula. The Crab Nebula is a supernova remnant. So the Crab Nebula was a star that turned into a supernova in the year 1054 AD, so roughly 1,000 years ago, and it was so bright in the sky, it was brighter than the full moon. It was visible during the day for like 2 weeks, which is kind of wild to think about. But the point is, like, that's still shining. We can still see it. So do you consider that still a supernova, or there's not like a discrete end where it's like, oh, it's no longer an exploding star. It's continuing to explode outward. It just gets larger and starts moving more slowly and isn't as bright. So yeah, I don't know how long it really lasts, but those are the timescales roughly involved in this sort of thing, I think. Anybody, again, feel free to correct me, but I think that's like rough timescales.
Yes, I think on an observational point of view, right, we observe supernovas a lot, and I think they're right. So they become extremely bright, right? We see them from other galaxies. Sometimes they overshine the entire galaxy in terms of like how bright they are. And the rising time is very quick. I'm not sure, like, I think it's at like terms of like hours or even minutes, like the way the supernova becomes extremely bright and then it slowly becomes less and less bright. And that I think it can last several days or months. So the supernova itself will last quite a long time. It will be observable for quite a long time.
But the really cool thing about supernova explosions to me is that, unlike almost everything else in astronomy, they actually happen on a human time scale. So you can actually, look at a supernova with your telescope and observe the entire thing. They take, days to weeks, months maybe, but you can observe them. Unlike a star, which is you can only observe in snapshots because they last for tens of billions of years. So that's what kind of makes the supernova explosion type of science really exciting. This is actually called transient astronomy because of the fact that they're so fast relative to lots of the other things that are happening.
Exactly.
And it's also very fascinating how like each phases, they last less time, right? Like what Margaret called like the adult life is when the star burns hydrogen in its core. And then it's the longest time for every star. And then the next element that it burns is gonna last less. And then it's gonna last less and less and less until like the last stages, the silicon burning lasts like hours, right? So you go from millions of years to hours. Yeah. So it really accelerates towards the end.
Great. Okay. Excellent job, guys. And we tuned in everybody from the panel into that one. That was great. So next question that's I posted in the chat. You can go to this Menti website and not just post your questions there, but you can upvote other people's questions. And so we get, again, kind of the most highly voted, the most desired questions, because there have already been 23 questions that have been posted, and I don't know if we're going to get through all of them, but so definitely we'll go through the list on the ones that are most highly upvoted. The next one that's most highly upvoted is, if binary stars are born in common gas disks, wouldn't they be roughly equal in mass, or are they born separately and find each other later? That's a great question. Who wants to handle this bad boy?
I can take a quick stab at it. So, generally, binaries are often equal mass because they are formed in a common gas cloud. They're not always exactly equal mass, but you generally don't get things that are really large, more than a factor of 10 different in mass. So usually they're pretty similar within maybe, a factor of 2 or so. There are certain special types of environments where you can occasionally form the stars separately from separate gas clouds and then bring them together after they've formed. And in there, you're not so much limited by the fact that they had to come from a common cloud, and you might have some different mass ratios. But those things where they form after they formed separately only happen in really dense systems. So, for example, like the ones that I study, dense clusters where stars are very closely packed and can encounter each other, not only as binaries, but as individual stars that just happen to be really close because of the high density of the environment that they're living in.
I guess a follow-up question related to that. In those dense environments, what kind of diversity in the size of the stars that are present? You said in the binary, you might only have a massive star that's maybe 10 times the mass of its companion, or closer, maybe 1 to 1, maybe 2 to 1, something like that. But in that entire like globular cluster or other environment where there's all these different stars, do you find more diversity, like maybe a star that's 1,000 times more massive than the smallest member, or 100 times? What's the rough kind of distribution of the masses or sizes of those stars in that larger environment?
You might get a little bit more of a disparity, but not that much. And the reason is, let's say you have one of these dense clouds of, 1 million stars. Okay, that's its own self-contained system. So, like anything that's governed by gravity, the most massive things are going to sink and preferentially interact with other similarly massive things, and the lowest mass things are going to float at the sort of outer parts of the system and interact with other lower mass things. So the things that form binaries with each other are, even though the way that they form binaries are totally different than the way you would form binaries from this common gas cloud origin that Margaret was talking about, because of this sort of mass segregation effect, you're still going to form binaries of generally equal masses. So generally maybe others can correct me if I'm wrong or missing things, but generally most of the binaries that we find are reasonably close to equal mass.
It's like you got a bunch of weird people at a party, and all the people who are like each other go and hang out and make a couple together. So you get like, the sports people go and hang out in their section, and then you've got the like book nerds hanging out in their section, and then you've got the like socialites hanging out in their section. I mean, based on mass, but that's okay. Poor analogy.
I would say that it's harder, right? When you think about astronomy, you always have to think about how do we find out things, right? How do we discover things? So how do we discover that there's 2 stars instead of 1, right? And if there's 2 stars and one is much dimmer, one is much smaller than the other one, it's gonna be hard for us to figure that out, that there's another star there, right? So there's also that bias a bit. We have methods to overcome that, but sometimes it's just hard to see that there's a bright big stars and maybe it has a very tiny companion. We'll never figure that out because it completely overshines the tiny companion, right?
Indeed. Okay, our next highly ranked question is, how long does it take a normal sized star like Earth's sun? Oh, wait, no, I already asked this, or I already answered this. Sorry, guys, moving on. If binary star systems are usually linked to supermassive stars, are there any known brown dwarf binaries or other low mass binary star systems? I mean, your presentation was primarily on massive binary stars. Do we also see low mass binary stars?
We do. I don't consider myself an expert on the low mass binary stars, and I think that the fraction of stars that are in binaries tends to be higher for more massive stars than for lower mass stars. But there are lower mass stars in binaries, and I don't know. Does anyone else know about the brown dwarf binaries? I don't.
Yeah, actually, the closest brown dwarf to Earth isn't a binary brown dwarf. And when something is the closest to you, it tells you a lot, because what's the chance that the closest thing to you is something if it's a rare thing? So yeah, binary brown dwarfs exist for sure, and there's tons of them.
Ilaria, is that the closest star to Earth, a brown dwarf? Or I guess it's an M dwarf that's Proxima Centauri.
Proxima Centauri is an M dwarf, yeah.
An M dwarf.
But the brown dwarf, this binary brown dwarf, I think it's very close. I don't.
It must be.
Because Proxima Centauri is only a few light years away, so.
Yeah, I think it's maybe Proxima Centauri is like 4, and this brown dwarf binary is like 6 or 7.
Okay. Cool. Okay. Great questions, people. Great questions. Keep them coming. During a black hole merger, does any radiation or spaghettified matter momentarily escape from the event horizon? Well, yeah, who wants to take this?
It seems like based on what we've seen so far, we haven't detected like the light radiation coming out when two black holes merge. I don't know. Kyle, do you know more? Like, is there any chance that we could have any, or is it just we haven't detected it yet, kind of a thing?
Yeah, so we've detected around 100 black hole. Okay, so first of all, I wanted to clarify something. The question, I think, is talking specifically about mergers of two black holes. Okay, so you wouldn't expect there to be any light because the black holes are black and they don't emit light. So we've detected about 100 black hole plus black hole mergers so far with gravitational waves. And the collaboration LIGO that's been searching for these has sort of partner electromagnetic collaborations that look for what we call EM or electromagnetic counterparts. So they've been trying very hard to find potential electromagnetic counterparts of these black hole binary mergers. And there's been a few claimed detections, but in almost all cases, they've been debunked and said it's actually not, a legitimate detection. The one exception is for actually, I think, the most massive black hole binary that's been detected yet. It had a potential coincident electromagnetic flare. Now, this flare did not happen at the exact time of the merger, but slightly displaced in time. And the thought there, maybe this is speculative still, is that the black hole binary merger happened within a very dense, not necessarily a dense, but within a gas-rich environment, and basically the merger product passed through a large sort of gas disk, which produced a flare after the merger occurred. So it didn't actually come from the merger itself, but if the black hole merger happens, where there's gas around, you could potentially get a related electromagnetic flare. But the current thinking, and this hasn't yet been, shown to be otherwise, is that from just a regular black hole merger where there's nothing else involved, you're going to get a gravitational wave burst, but no light.
Great response.
Thanks.
Okay. Unless you guys have something else to add on that one, I'll move on to our next.
I think the question was if it comes out of the event horizon, right? And I think the point here is that, no. you need, what Kyle was talking about is like material around, right? You can have material around that emits light, but from the black hole themselves, nothing can escape from the event horizon. That's kind of like the definition.
Like the physical law of the event horizon. You can't allow that. And sure, you can tweak things a little bit when you get into a very extreme gravitational environment from another black hole proximate to your existing black hole, but it's not going to open up a hole in the event horizon that allows stuff, either material or light, to escape. So yes, everything that Kyle said was relevant and true, but yeah, he was primarily referring to the accretion disk or the material surrounding the black hole itself. And so yeah, formally nothing can escape from, unless you're in a movie called Interstellar, and then all information is all bets are off at that point. But okay, our next question, I somehow must have deleted it from audience member Chris Georgi. Is there a scenario in an interacting multi-star system in which a supernova produces a remnant other than a black hole or neutron star, or even leaves none at all, nothing at all after that supernova?
Well, go ahead, Margaret. Sorry.
Oh, no. I mean, I guess I would say I don't think that there's a situation where you could have not like a neutron star or a black hole after a supernova. There are situations where you might just not get a supernova at all, and you could have a star that directly collapses down to a black hole without the explosion at all. As I kind of showed in my talk, that the kind of star to supergiant to supernova to neutron star black hole, it's like a little bit more complicated. And we think that there's kind of like some ranges of mass where you have a neutron star, somewhere you get a black hole. But I think like if it's massive enough to undergo a supernova, you should have a neutron star or a black hole left after that. I don't know, Ilaria, are we going to add something else?
No, I just wanted to say this. We call supernova, unfortunately, a lot of different things. So there is actually a type of supernova that doesn't leave anything, but that's not a supernova the way that Margaret explained it. So it's not what happened at the end of a star's life, but it's actually when a white dwarf explodes because it becomes too massive. So we call that type 1a supernovae. And, you know, the thing it calls supernova anything that it's extremely bright and, you know, it was not in the sky until yesterday and all of a sudden it's in the sky, right? So it's a nova, it means something new, and super because it's extremely bright, right?
Super new.
Super new and super, exactly. So for example, type 1a supernova, it's an all different thing. You know, you have a star like our sun, or, you know, a bit more massive, but not much more massive. Gets to the end of its life, becomes a white dwarf, and then it has a companion. And so it might accrete some mass, or it might merge with another white dwarf. There's different possibilities. And then the mass is just too much for the white dwarfs to survive. And then it explodes. And that's like a thermonuclear supernova. And that just starts from the center of the white dwarf and completely incinerates it. So it doesn't leave anything at the end.
Yeah, I don't know of any other.
There's one other kind of rare thing that people talk about for really massive stars, which is called a pair instability supernova. So there, the idea is that the center is so hot that you produce a bunch of electron-positron pairs that basically annihilate and produce so much energy that it triggers a runaway and completely obliterates the entire star, core included. So the idea, and these haven't been actually observed. There hasn't been a clear observation of one of these. So it's not observationally confirmed like a lot of the other things Margaret was discussing, but it's suspected on a theoretical grounds that you could potentially have a range of massive stars where you might get one of these and leave nothing behind.
And the theory is pretty solid. Sorry?
The theory is very solid, is that what you said?
Yeah, it's pretty solid. Like we do expect some range. I mean, maybe the definition of the range is not super constrained. But one thing is that we found black holes that are in this gap. We expect no black holes to be in this gap because, you know, you have this pair instability supernova and they don't leave anything. But we found some. And I think Kyle, did you work on this, right? Explaining how you can actually create those without a supernova?
Yeah, well, so one of the, just to sort of step back for a second, one of the really exciting things about the gravitational wave events that LIGO has observed is they give us information on actually what's left after the supernova for really massive stars. So, you know, for lower mass, kind of massive, but not really massive, they leave behind a neutron star. And we can observe neutron stars, you know, pulsars, millisecond pulsars. But for the really massive ones that leave behind black holes, we didn't really have a way of observing the remnants that were left over until the sort of dawn of gravitation, the gravitational wave era. So the really kind of weird thing about the black holes that LIGO has observed in gravitational waves is there seems to be kind of a cutoff in the mass. So actually, Margaret showed one slide with that. It kind of looks like the slide kind of looks like a manta ray, the way that all the compact objects are sorted out. But we see most of the LIGO black holes are less than roughly 40 solar masses, 40 times the mass of the sun. But there's a very small handful of events, like 5 or 6, that are more massive than this. So nearly like 80 times or even up to 100 times the mass of the sun. Actually, I think 90 is the most massive that's been observed. So these small handful of events are really weird because these are in this sort of what we call mass gap, where we don't think black holes would have formed because of this pair instability supernova I mentioned before. So I'll say briefly, one way we think these weird mass gap black holes might form is if you have a black hole merger in a dense environment, like a star cluster, And if the black hole that's formed from that first merger stays in that dense environment, then it could potentially find another black hole partner, form a new binary, and merge again. So then because you're forming new black holes from the previous mergers, you can potentially fill the mass gap by repeatedly merging black holes. So that's one potential idea for how this, again, small number, roughly 5 extra massive black holes might have formed.
Well, we still, just to chime in, we still don't understand how the supermassive black holes formed so quickly. The ones in the cores of galaxies that are 1 million or 1 billion solar masses times the mass of the sun. And we observe those very, very early in the development of the universe in the first, few 100 million years. And we don't know how to merge black holes on the stellar scale to be this like 1 million times the mass of a stellar mass black hole on such a quick time scale. So that's definitely an area of active research that's being conducted, especially with the help of something like the James Webb Space Telescope. So hopefully we'll better understand that soon. Yeah, great answers, guys. Oh, and I encourage audience members, I know you guys have that Menti link that I posted in the various places. So people are continuing to ask questions, and there's a lot of ones that have been asked in the last 10 or 15 minutes that you should check back. And I think you can have it sorted by recent questions, and you can see if any of those are interesting that you might want to upvote beyond some of the, right now, all the highest voted ones are, I think, the earliest because they've had the most eyes on them. So I encourage people to check that out, but there've been some really good ones recently. Okay, our next most highly voted question is, theoretically, what would be the shortest possible lifetime of a supermassive star? I guess this plays into what we were just discussing. And how would its evolution look like in terms of time, like accretion and then ignition into a supernova and then collapse or something like that? So what is the shortest, I guess, what is the most massive star that could exist by our own estimates? People, we were just talking about, above some limit into, our sun is like a typical size star. I mean, what do you say typical, right? There's this whole range of different stellar masses, but definitely as you get more massive stars, there's fewer of them relative to the little tiny guys that are out there. But how large can we go? How massive of a star can we form before it just gravity doesn't work on that scale and it fragments into 2 smaller clumps or multiple smaller clumps instead of that big boy? It's like 100 solar masses. We think that POP3 stars, like the first generation of stars, were very massive. I thought like on the order of 100, but.
Well, we have observed a few that are a few hundreds.
Okay.
But the problem is that they last very, very little. And I think there's been a lot, well, maybe you guys know better, maybe Margaret should answer this, but I think there's all this debate of like, in the very, very early ones, there might have been, thousands of solar masses one, and that might be why these like huge, supermassive black holes formed, is that they came from extremely big stars. But those are like, I think, theory that have not been confirmed.
Looks like a super Humvee. Yeah.
Semi-truck.
Like a tank or something.
Yeah, it's like a tank, exactly. So yeah, with that first generation of stars, if they were, or I guess any stellar object that's like 1,000 solar masses, presumably its lifetime would be extremely short, right? Because it's compressing things with so much force, the interior, that the temperature gets really high and it can just burn through that fuel extremely quickly. So it would be very bright for a very short period. But I wonder what sorts of timescales, like even O stars are most massive, like 40 or 50 or 100 solar masses. What are their lifetimes? I thought it was like 5 million years.
Yeah, like a couple million can be like the really short ones.
So maybe these really super Humvee tank stars would burn through it in less than 1 million years, which I guess to our audience, 1 million years, like that's a long time for a human, but like for astronomy, that's nothing. The age of the universe is like 14 billion years. So like 14,000 times longer than a million years. So that's a million years is like period.
Yeah, I think for like those 100 things, the small handful of stars that are observed that have life that are, you know, over 100 times the mass of the sun, I think the expectation is they're about a few million years. So that's about as short as, like, at least for the stars we've seen that are confirmed, that's about as short as you can get realistically that we know of.
How short? What was it?
A few million years.
A few million. Great. Good job, team. From the X-ray images that Margaret showed us, how do we know the object is what we think it is? That is, you know, co-located compact object and not just something else that we can't recognize or something like that.
That is a really great question, and one that we spend a lot of time trying to make sure that we find the answer to. So there's like essentially what we do is with the X-ray telescope, we're detecting what we call like a point source. So you could have something that would be more extended emission from like X-ray emission, where that might be coming from something like a supernova remnant, which we talked about. So that would actually like take up kind of space on the sky versus looking like a pinprick of light that kind of is like spilling out in a circle around it. So we're kind of like, first of all, we're looking for that. And then we kind of expect that the light coming from an accreting black hole or neutron star, the spectrum, or kind of like how bright it is at different energies of X-ray light, should kind of have a characteristic shape. And we kind of expect that it's what we could call hard X-ray, like it's like hard, which means that basically it's emitting like kind of like the ratio of high energy X-ray photons to low energy X-ray photons. Kind of, we're getting like a lot of these high energy photons. And then there's like a lot of tests. I mean, there's obviously some chance when we're kind of matching up these optical images with the X-ray images, there could be like a chance, what we call like a chance superposition. So you could like happen to get a bright blue star like right at the location where you see these X-rays coming from an accreting like black hole or neutron star. But the chances of that tend to be pretty low, just because really bright blue stars that are massive stars are not that common. So, you know, we think that the chances of that happen might be like 1 or 2%, that we would have kind of like an accidental overlap there. So yeah, and sometimes we could see like this X-ray emission. One thing that's kind of interesting that we see sometimes by accident is we'll actually see X-ray emission coming from a supermassive black hole in a really far away galaxy that we're actually looking at through the galaxy that we're trying to study. So like we're looking at Andromeda and we think that this, you know, point source of X-ray light is in Andromeda, but we realize actually it's something that is much further away that we happen to just be seeing kind of through the disk of the galaxy. So these are kind of all things we have to kind of rule out by doing kind of various tests to confirm that, you know, this thing is actually in the galaxy we think it's in, and that, you know, we have to figure out kind of what is the chance that maybe it was like, you know, they happen to be like kind of co-located but not related, kind of a thing.
Great explanation.
Thanks.
It sounds like a really tricky problem. Makes me glad I'm not an observer.
Well, it's funny thinking about like, you know, I feel like in astronomy, there's so much of like one person's trash is another person's treasure, you know, where it's like, for us, we're like, oh, these background like AGN, or which are like, you know, these supermassive black holes in galaxies, where like, these are just contaminating our sample. And then other people are like actively trying to find these things. You know,
so. Margaret, what is your favorite phase of massive binary stellar evolution?
So I guess I'd probably say the high mass X-ray binary phase. That's what I spend all my time thinking about.
And so, okay. So when both, because you described all kinds of different configurations. So you'd say for the high mass, you'd say two massive systems, or you'd say like a compact high mass system like a neutron star or an X-ray or a black hole with another neutron star or a black hole, or a neutron star and black hole with like red giant system, or what?
So it's like a neutron star or a black hole with a high mass star. So the high mass star, we kind of find like typically is like a main sequence or like a regular star, but we do see them also in like supergiant phase. So it kind of depends. That phase just lasts like less time, so we don't find as many of them. And then the reason we call it a high mass X-ray binary is just because the high mass refers to the mass of the companion star. So there are also X-ray binaries where the second star that's not like there's the black hole or neutron star and then the second star, and that star, those we see these systems where the second star is a low mass star. It's kind of more similar to our sun. But the systems that I study are the high mass ones where, you know, that one could eventually also turn into a black hole or neutron star.
Is the black hole field Laplacian? Do we observe quantum gravity fluctuations that could prove quantum container and lensing? Whew. Who wants that? I don't want to do this. I don't know the answer to that. Do you guys know that answer?
I don't even know what quantum container is.
Neither do I.
I mean, Laplacian, is the Laplacian field something that is like incompressible or something? It's like a vector field that is incompressible. But would that be like gravitational field? I guess black hole field would be the gravitational.
Right. What I would encourage the author of this question is to wait 1 month until we have Saul Tucholsky, who is a numerical relativist who deals with these sorts of things, and, you know, modified gravity or the extreme gravitational fields associated with black hole environments and that sort of thing, and he'll give it to you straight. But none of us
He is probably the best person to ask. One of the top 5 in the world to ask that question too.
Yeah. So I'm sorry, I don't work on that. That's my cop-out response. But yeah. Bring it back in a month for Professor Saul Tucholsky, who works explicitly on stuff related to this. And he might know what a quantum container is, because I don't know what a quantum container is. Okay, sorry. Let's see. Can Margaret Lazzarini speak on the number of generations of stars? Somebody said that our sun might be a 3rd generation star. What's a good upper limit of stellar generations over the lifetime of the universe? Like a dozen, something like that? Good question. Good question. I mean, we talked about like population 3, population 3 implies that there's population 1 and population 2, but it goes the reverse order that you might think. So yes, astronomy is all riddled with these kind of weird statements. A population 3, when we talk about population 3 stars, it usually means the 1st generation. So I guess like the larger the number, the farther back in time they formed. But those were thought to be the original stars that formed out of the primordial elements that were present in the universe at that time, the hydrogen and the helium that were present. There were no heavier elements, what astronomers call metals, but heavier elements consisting of oxygen or carbon or iron or other things. And hydrogen and helium aren't very, very good at cooling and radiating away energy. So these stars form kind of slowly. And as we discussed, we think they tend to be more massive. At least the computational models that we've done of these things tend to be much more massive than normal stars. So 100 to 1,000 solar masses, something like that. But eventually those stars exploded, at that mass they would have exploded. They would have exploded in supernova, and they would have largely kicked out some of the material that they'd been fusing in their cores that were forming those heavier elements like carbon and oxygen and nitrogen and everything else that we know about on the periodic table. And that went into the surrounding gas. And then from that gas, you were able to form the other generations of stars. So then you formed the population 2 stars, which are, again, like the generation after the 1st generation. And then eventually you can form something called like population 1 stars, which our sun is a population 1 star. In terms of number of generations of stars, that's a really good question. I guess it depends on, what the mass of the star is, because the higher the mass of the star, the faster its evolution, the faster it explodes or expels out its enriched material from its core that it's been fusing and producing these heavier elements. But I mean, generally we refer to these as like three populations. Population 3 being the first stars, population 2 being the next generation of stars that are a little bit enriched with some of these heavier elements that formed in the cores of those first stars, and then the population 1 stars that are formed from the further enriched material that kind of populates the gas throughout the present day universe. Does that seem reasonable to you guys? I'm not just like, this isn't really my area, so.
Yeah, but we were talking about these very massive stars that live like a few million years. If you think about that, stars, there's been many generations, right? So it's I think the way you describe the different populations is more like how many of these metals, how polluted the gas that formed the star is, right? And
so it's a continuum, really. It's not like, all right, all the stars explode now, and then we'll form a new generation of stars. Now all those stars explode now. So it's not a discrete thing. It's just, it's referred to as 3 populations, but as Ilaria says, it could nominally be many more generations of.
I mean, if you look at it in a specific part, for example, in globular clusters, where you have all the stars that are kind of born at the same time, right? And so in those environments, then you can have several, we call them several populations, which are several generations. So it's different bursts of star formation. And so, for example, there are some globular clusters that have maybe 2 or 3 different distinguished kind of generations, right? And you can actually see it. We can actually observe this. They're like, in 3 different ages somehow.
All right, reading our next question from the upvoted list. Can the James Webb Space Telescope detect a supernova from the earliest time after the initial Big Bang? The earliest time, okay. Thank you. Excellent discussion by a team of excellent scientists. Oh, well, happy to provide this. So I guess the question is, can the newly launched James Webb Space Telescope, which just kind of completed its focusing of the individual mirror segments last week, so should start taking science data very soon in the next few weeks. Can the James Webb Space Telescope discover a supernova from just after the Big Bang? And the answer is no, because there are no supernovae formed right after the Big Bang. That's the short answer. It takes a while to form that first generation of stars. And then once those stars have formed, we just talked about, like, they can be very massive and they can undergo supernova explosion really shortly after that, like 1 million or so years. But the time scale between the formation of the universe and the beginning of the universe in the Big Bang and the formation of the first structures, these first stellar structures, what's the time scale estimated to be? Redshift of 15 to 20 is when POP3 stars form. That's like in the first 100 million years after the Big Bang, I think, roughly. Which again sounds like a really long time, but in the broader picture of the fact that the universe is like 14 billion years old, it's not particularly long. But yeah, initially the universe is just this really hot, dense environment that's pretty uniform in its distribution. Like, it's like looking through a fog of stuff. Everything's pretty uniform, but there are slight overdensities and slight underdensities. And as time goes on, gravity, which is an attractive force that pulls 2 objects that have mass towards each other, those slight overdensities pull themselves into slightly more overdense regions. And so that turns into a runaway. It's kind of like the rich get richer over time. Well, these overdense regions, they pull more stuff into them and then are more effective at pulling even more stuff into them. So those become the seeds of the first structures, the first galaxies, the first stars, and so on and so forth. But that takes time. And the amount of time that it takes is on the order of like 100 million years. Do we see supernova from that period? Not yet. we see galaxies, we see, we see like the quasars in the centers of galaxies, not the first generation of stars, kind of the second and a half generation of stars, but we don't see the first, or I'm sorry, the first and a half or the second generation of stars, but we don't yet see the first generation of stars, at least that we know of. But that's one of the things that James Webb is kind of trying to do moving forward. I don't know. Do you guys want to add anything? I don't mean to hog the question.
The highest distant supernova, I think I remember like, but it must be like many years. There was one detected at redshift 4. So
Oh, that's the highest we've gotten is only redshift 4? Oh.
No. I'm talking, but it's probably old information. I know.
No, I mean, that's perfectly reasonable. I mean, the things that we see at we're using jargons called redshift, which effectively is how
12 billion years ago.
What's that?
12 billion years, right?
Sure.
Redshift 4.
Redshift 4?
What is redshift 4?
Yeah, maybe a little higher. Maybe like 12 and a half. Anyway, a long time ago, which is to say a long ways away from us. And yeah, the things I was talking about is we can see the supermassive black holes in the center of these galaxies because stuff is falling onto them and they're kind of burping and we see the light that comes from that burp. But yeah, I guess in terms of actual supernova, you're probably right. It's probably not as distant as those bright sources in distant galaxies. So we haven't yet. We haven't been able to see, the answer, I guess, is we haven't been able to see supernovae just after the birth of the universe. It takes time for the structures to form, and our telescopes aren't yet powerful enough to see individual stellar explosions at that distance, over that distance. And but yeah, again, James Webb will start to reveal more on that front. Would a common envelope, this is relevant to the presentation that was just given by Margaret, would a common envelope scenario be possible not just in a binary star system, but in a triple or like a quad star system? Could you have that single envelope that the stars all kind of like fall into, and then they have a big layer surrounding them?
I would say that would be very hard to have actually happen, just because it's hard to get all the stars in that close without them kind of like, yeah, one of them getting like chucked out. I feel like Kyle could probably talk more to
or
exactly
just
how that happens, but
yeah, or just merging. I mean, if you get them close enough to, have a triple common envelope, it's very likely they would just physically collide with each other.
Yeah.
So I think usually in like a triple or a quadruple system, you're more likely to just have a pair. So a lot of times these, like a triple star system is what we call a hierarchical triple, which means it's you have your inner binary like this, and then you have your third star out here, trying to make sure everything's visible. So you have your inner binary here, and then the third star is sort of a binary where the other companion is actually the inner pair of stars. So a lot of times what will happen is you'll have a common envelope in that inner pair, and then the third object is out there just doing its own thing. So it's pretty rare that you'll have all three or all four stars interacting actually at the same time.
All right, moving on. Electron degeneracy pressure. Which of the four fundamental forces counteracts the gravitational force in a white dwarf star so that it doesn't become a neutron star or a black hole? Okay, getting pretty detailed. So I guess, yeah, a white dwarf is held aloft because of the electron degeneracy pressure from the individual electrons not being able to get close enough, right? Because of quantum effects like the Heisenberg uncertainty principle. So what's the question? Which of the four fundamental forces is actually the thing responsible for, the Heisenberg uncertainty principle and the Pauli exclusion principle that prevents these electrons from collapsing on top of each other?
I don't think it's an
Not a
actual
physical
force. It's the same. I mean, if you think about pressure in a gas, right? Of course, that can act force on, if you pressurized gas inside something, that acts a force, but it's not really one of the fundamental forces. It's just pressure, right? The same type that when things are hot, they move very quickly. The particles move very quickly, and then they apply pressure. The gas of which the particles are made of apply pressure on I don't know, the boundary of where the gas is, right? Whatever the box where the gas is. And I think for white dwarf, it sounds very strange because you think, oh, it's the electrons that are applying that pressure, but it's not really any of the fundamental forces. It's not the weak force or the strong force or electromagnetism or anything. It's a direct result of a principle in quantum mechanics that you cannot have. No, it's like if you have two electrons that are very close, they cannot be in the same energy state, right? So all of the lower state, if they're full, if you put another one, it's going to have to be more energetic. So it works like if there was a temperature, like if there was heat, if you have particles in a gas, you apply more heat, they go faster, they're more energetic, and then the gas, applies more pressure. Right. The same in a white dwarf, you put another electron, there's no heat involved. It's more like this weird quantum mechanical thing. But if you put in another electron, then that electron will be more energetic and put more pressure and et cetera, et cetera. And that's what keeps white dwarfs up. So it's the same as in normal stars, what's creating that pressure is the nuclear burning. The nuclear burning generates a lot of heat, and that heat makes the particles of the gas very energetic, and that's what keeps up the star. In this case, what makes the electrons very energetic is this quantum mechanical principle, and it's due to the fact that the density is extremely high, much higher than in a normal star.
Right.
It was a very technical.
I think that's good. I think that explains it much better than I could have, certainly. It's a good question too. Like how do quantum effects figure into the four fundamental forces? They don't. They're kind of parallel to it anyway. What background does an undergraduate student need to get into early research in binary systems, specifically for theoretical or simulation projects? So presumably our audience member is perhaps an undergraduate student who's looking to get into research into astrophysical things to be involved in. Maybe you have a new student on the way, Margaret. Maybe someone's like, I love that so much, I'm changing fields, I'm going to pursue this and be your student. So what do I need in order to prepare in terms of coursework or experience to get more involved in this field?
I mean, I can take a first stab and then other people can join in. I mean, I think, in to do research in astrophysics, I think that kind of one of the primary skills that you need to have is being able to program. And so I think that there's so much that you can kind of learn like on the fly, like learn kind of like while you're working on a project. But I would say like maybe taking like an introductory like computer science class would be like a really great place to start to kind of like tee you up to be able to like be at a place where you could kind of jump into a research project. And then I think, in terms of coursework, again, I don't know. I mean, I think everyone kind of maybe has different thoughts, but I think getting involved in research like as early as you can is a really great thing to do. And I think that, you can kind of engage in research at the level you're at as an early undergrad. And then as you take more and more classes in physics and math and astronomy classes, I think you can kind of like deepen your understanding. But I think there's like a lot you can learn just kind of like jumping in on a project and like really starting to like learn kind of that niche of the field and kind of the background you need to get going on that.
And there's also, that this depends a lot on where you are in this, where this person is in the world or which
right.
universities. Like some universities very easy to have opportunities to jump into research very early. Like at Caltech, there's all these programs that you can do summer research and things like that. Where I did my university, for example, it wasn't like that at all, right? And so one way, you have to be very proactive if that's the case. If you really want to, you have to look around and look at opportunities, look at summer projects, maybe outside of your university, just check online and just put yourself out there, contact professors directly. Many of them will not answer because they receive so many emails. It's okay, it's not personal. It's just sometimes professors don't answer, or like just that maybe try to email the postdoc or even the grad students and things like that. Just be proactive. I think that's important.
Just to say one other thing in terms of like, the types of technical like classes you maybe would need to have taken first. You actually might be very surprised that, a lot of the research we do can be done with only, undergraduate level physics type classes. It doesn't necessarily take, there certainly are branches of astronomy, like, string theory or very advanced, general relativity type things that take years to develop the skills for. But for a lot of the stuff we do, you really don't need much beyond, high school or maybe a first year of college level classes to really start, getting a grasp of the theoretical side of the problems. So I would second what Margaret said. I think having some background in computer programming and computer science is probably the single most useful thing, the single most useful skill to sort of contribute and be able to get involved in research.
You're here. Yeah, I stumbled into astronomy. I studied computer science as an undergraduate and then transitioned to doing astrophysics after. And I'm glad that I did. I have, more background in doing algorithm design and that sort of thing that I think really comes in handy for modern day science. It's just like so much coding. So
I feel like I had almost the opposite. I took a semester of programming in undergrad, but I feel like it was a steep learning curve for me when I got to grad school. But I feel like it just kind of proved though that like you can kind of just like pick it up if you just kind of jump in.
Yep. Just be patient with yourself, and as you say, it can be steep, but definitely rewarding once you get into it. All right, next question. What is the remnant when two white dwarfs merge?
I can answer that. I work exactly on that. No, it depends on the mass of the two white dwarfs. Again, when you study stars, you're gonna hear this answer a lot. It depends on the mass. It depends on the mass. Everything depends on the mass. But the idea is that, jumping back into the electron degeneracy pressure, white dwarfs are strange because they're not kept up by nuclear burning like normal stars. They're kept up by this strange quantum mechanical thing against gravity. If there wasn't this strange quantum mechanical thing, they would collapse, right? But the electrons can sustain only up to a certain mass. If the thing becomes too dense and too massive, even the electron degeneracy pressure cannot sustain the star anymore, and then it collapses, right? So when the two white dwarfs merge, if they're small enough, small is a wrong word, but if they're massive enough, so if they have less mass than this maximum mass that the electrons can sustain, this mass is about, let's say, 1.3 something solar masses, so about the mass of the sun plus 1/3, or then if you sum the mass of the two and it's less than that, then they merge and they create another white dwarf. So which is going to be strange because it usually rotates very fast. It might have a very high magnetic field due to this like very energetic birth, but it's just a white dwarf. If it's above that maximum mass, then it explodes. And then it's what we were talking about before. This is called type 1a supernovae. And those are the ones that just explode and doesn't leave anything. Because, you know, the burning starts from the center, the explosion starts from the center of the stars, and then it just destroys everything. So yeah, these are the two scenarios. White dwarfs, there is the possibility maybe that, you know, if you can stabilize it enough, it does collapse, but not explode and become a neutron star. But that's I think the actual merger of two white dwarfs is probably too energetic for that to happen. You usually have a type 1a supernova. So it's, you know, the mass is lower than something, the remnant is a white dwarf, the mass is higher than something, the remnant is a type 1a supernova explosion. Yep.
I learned something today. Excellent. Thank you, Ilaria. Okay, next question. Through observation, how is it possible to differentiate between stars and the accretion disks? I guess accretion disks around stars? Does the disk emit different emission lines than the stars itself?
I think it's referring to like in the high mass X-ray binary systems. I think like how do we differentiate between whether we're looking at emission from the accretion disk or from the star?
Sure.
And so yeah, they do emit different emission lines, and they also kind of, the peak of their emission happens at different energies of light, and that basically is dictated because the accretion disk is really hot, so it's going to be emitting the vast majority of its emission at X-ray wavelengths, whereas the companion star is not quite as hot. I mean, it's still very hot. Like the accretion disk is like millions of degrees Kelvin, and then the star is like tens of thousands of degrees Kelvin. So there's like this kind of difference. So the star is going to be emitting most of its light at like optical wavelengths, which is, you know, the type of light we can see with our eyes, and a lot at ultraviolet. I mean, you know, there is some like kind of wavelengths where you might be getting some emission from both. And that is kind of like an interesting thing that I think, you know, is like kind of a challenge, is something we're kind of, that's like people are still thinking about, because you could still, you know, even though an accretion disk is emitting most of its light at X-ray wavelengths, it's still going to be emitting some at like ultraviolet wavelengths, and you might get a star that's emitting most of its at optical wavelengths, but it's also emitting some at ultraviolet. So you can kind of have this like ultraviolet like contamination between the two. But generally when it's, you know, we kind of expect to see like the peak of where this emission's happening at different energy ranges. And then the emission lines would also be different. I personally haven't done a lot of like spectroscopy, which is where you're actually like taking the light and like dispersing it. So that's where you would see emission lines. But yeah, we would see different emission lines from accretion disks and from stars, definitely.
Great. Comprehensive response. Thank you. In a binary system, can one of the stars in the binary get kicked out when one of its members goes supernova or black hole? And if so, how would that work? I guess you kind of, you explained this, but it might be worthwhile to just, you know, quickly re-describe it.
Me?
Yeah.
Yeah, I mean, yes. So one of them could get kicked out during the supernova. Sometimes you could expect like when a supernova happens, you get something called a supernova kick. So like there can be kind of like this velocity that's like imparted on the thing that just had a supernova. So sometimes that could disrupt the binary, or it could kind of, sometimes the binary will stay as a binary, but the whole thing will kind of get like kicked in a direction based off of that supernova kick. So yeah, I think it can happen. And that's kind of like what I was saying, there's a lot of like phases where stars could like kind of just like drop out of this binary evolution process. I mentioned mergers is kind of one of the main ways that it could end, but you could also get the binary could just be disrupted in the stars.
Ejection or disruption is one of those ways.
Yeah.
I see. what could be the role of the James Webb Space Telescope in the study of binary stars moving forward once it starts actually operating and doing science data? Will it be able to provide any kind of interesting results pertinent to binary stars, or is it just?
That is a really good question. I think, I'll say I honestly can't feel like I can speak too much to like every other like phase of binary evolution. I think for high mass X-ray binaries in particular, I don't know, like I don't think there has been like, I don't know that much about how we can study them with like the infrared light, which is what James Webb will be primarily observing in. I do think that one thing that's going to be really exciting about James Webb is kind of understanding like the galaxies, like where these systems are forming. And that's like a big piece of understanding the systems themselves, is kind of tying them to like the galaxy, like Andromeda, right? We see high mass X-ray binaries in Andromeda, but we want to understand like what's the kind of like feedback of like, what is the galaxy like? So like, what's the enrichment of heavy elements in that galaxy? What's its history of like when it was forming stars, and how does that compare with like the ages of these systems we're seeing, or the numbers of these systems we're seeing, or kind of like the distribution of like what types of stars and what types of compact objects we're seeing. So I think James Webb will be really powerful for that. I don't know. I'll open it up if anyone else has other things they want to say about James Webb and binary stars.
But there's a lot of a peculiar type of binary stars, like symbiotic stars, and all different kind of stars. I don't work on binaries, but I've heard of these, and those are very interesting to look at in the infrared, because they have like these transient events, like outbursts and things that they get very bright in the infrared, and often in the galaxy, they're very obscured in the optical, which means there is a lot of like gas and dust in front of the star because it's very far away, and that dust absorbs a lot of the optical light, so they're hard to look at. It's hard to look at them in the optical, but it's great in the infrared. This stuff is transparent, or almost, and so you can actually see these objects that you would not be able to do with optical light. Another thing is like, for example, the center of the galaxy, or globular clusters towards the center of the galaxies. That again, they're very extinct, which means they're blocked by gas and dust in the galaxy, but we will be able to see them. For example, this some globular clusters that have lots of X-ray binaries, and they're very active in the X-rays and gamma rays, but we cannot observe them in the optical because, again, of the gas, but we will be able to observe them in the infrared. And so that's going to tell us a lot about these environments, and the binary stars and the X-ray binaries inside these environments.
Okay, we've got about 5 minutes left, and I think we can get to a couple more questions. Actually, there's 2 more questions that I think we could get to. One is, are there antimatter stars? Everybody talks about we're made of matter, but we can produce antimatter in certain particle accelerators, and then form anti-hydrogen and form anti-protons and anti-electrons, and so on and so forth. Do we know of any antimatter stars out there? And how would we even know? I don't think antimatter has, aside from being like reverse charge, an anti-electron is a positron, right? So instead of having a negative charge associated with an electron, it has a positive charge. And an antiproton is similarly, normally a proton has a positive charge, an antiproton has a negative charge. And so when these things run into each other, boom, they annihilate each other, and there's a big explosion of gamma ray energy that comes from that sort of thing. So could you have substantial amounts of antimatter in the universe? Debatable. But is there any difference in its observational signature?
I think when the universe was very dense, if there was any antimatter, it would have been completely annihilated. I mean, how do you create it? You don't, it's very hard to create antimatter. So how do you create a star made of antimatter? Like it would have to come from, the primordial gas, etc., like all other stars. But at that time, since the matter is much more abundant in our universe, any fraction of antimatter would have been completely annihilated when the universe was dense and hot and plasma, etc., etc. So I wouldn't, nature always surprises you, but I wouldn't expect to see antimatter stars out there. There's been a lot of talks about like strange stars, which is like stars that in which like the protons and neutrons are kind of like melted into their components and things like that. Neutron stars, maybe some of them are strange stars. There's people that think about that, and very weird type of stars. There's lots of theories and possibilities, but I think antimatter, I don't think anyone has ever proposed it.
Sounds reasonable to me. That's a good explanation. Okay, so our final question of the night for each panelist, what's the astronomical phenomenon that knocked you out of your socks in the last year, like the weirdest thing you read about? Yeah, I don't know. I have to think about this.
In the last year.
Yeah, I mean, we could expand it. We could probably,
Yeah.
I mean, I don't know. If there's something that's more appropriate that's like a couple of years or a few years back, I think that's fine. But what's just like, I guess the audience member wants to know, like, what's something that we're surprised about? What's something that, I mean, we read a lot about this stuff and new scientific results. So what's an interesting result? I have something that I can say. So I'll let you guys have a few more moments to think about your own personal things. And I talked about this a little bit at the Astronomy on Tap earlier this week, and that is a few years ago, I think it was 2018 or 2019, there was the supposed discovery of galaxies that lacked dark matter. Normally, we think you have to have dark matter that holds the additional mass from dark matter, provides additional gravitational force to hold together large-scale structures like galaxies or clusters of galaxies. And essentially every galaxy that we've ever discovered seems to require or have evidence for a substantial amount of unseen mass in the form of dark matter on the order of like 100 to 1,000 times the amount of dark matter that's present is relative to the amount of like normal matter, protons and electrons and stars and gas. But now, yeah, there were a couple of results that seem to suggest that there are galaxies that don't require that don't have evidence for dark matter to be present. And in fact, we put out a Nature paper 2 weeks ago that shows some computer simulations that can also demonstrate that there are galaxies produced in a weird way. It's not like every galaxy, it's like some small fraction of galaxies that also, in the simulations don't seem to have any dark matter. Essentially, the dark matter got stripped out of them from these dwarf galaxies that passed too close to a more massive galaxy, and so it kind of ripped out the dark matter and just left the highly gravitationally bound stars and gas. So I think that's pretty weird and unexpected and interesting. But what do the other panelists have to say? What do you got? What's a weird result that you guys found?
Well, I can actually, for me, it's like something I worked on that really shocked me when I found out. So I was, I worked in white dwarfs, and I worked on I look for the merger remnants, that the question from before, like the remnants that are of like the merger of two white dwarfs. And those are like peculiar one, as I said, because they rotate very fast and have like very strong magnetic fields. And I remember when I found this one, it was like rotating every 7 minutes and had like huge magnetic field. And then I got a grasp of the radius of the white dwarf. And I was like, oh my gosh, because white dwarfs are like the size of the Earth or a bit bigger, 6,000, 7,000 kilometers in radius. And this white dwarf that I found, it was like the size of the moon. So like 2,000 kilometers. And so I was like, oh my gosh, what's this? So that really it made my head explode. And
Yeah,
that was like, yeah, 2021, so last year.
Wait, what was it? How was it so small?
It's very, 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 very massive. It's, there's more massive the white dwarf is, the smaller it is, again, because of the fact that the electron keeps it up. So to have more pressure, you have to squeeze them even more. And so, the more mass you put, you have to squeeze them more to sustain it. And so the more massive the white dwarf, the smaller. And so this one is very, very close to the limit of collapse. If it was, a few hundreds of kilometers smaller in my collapse, it might even collapse as it is. That was
a little bit more stuff on there, and it goes. Woof.
Yeah, it could either collapse into a neutron star or explode. We don't know.
Ah.
Because this one is kind of stable, and it's not like if you have the merger of two white dwarfs, then it's so dynamic that if it's above the maximum mass, you expect them to explode. But if it's just one white dwarf and it put a little bit more mass on it, it might actually collapse into a neutron star. It's called accretion-induced collapse, and it's a theory of like how some neutron stars are formed.
Do we have observational evidence for that occurring?
We do, because we have, for example, young neutron stars in old populations. So neutron stars usually form, when a massive star dies, and they don't, that's like a few millions of years, maybe a few tens of millions of years, right? Before the neutron star is born. But if you have a population that is like billions of years old, and you see a young neutron star, like how did that neutron star? It's not just coming from that population, from a single star. It might have been that there was a white dwarf hanging out, and then all of a sudden it collapsed into a neutron star, and that's why we see that it's young. So we have some indications that can happen.
Huh. Interesting.
So I can maybe piggyback off that, because that's related to what I was going to say was my most interesting thing that I saw in the last year. So I was saying I work a lot in these dense environments like globular clusters, which are, as Ilaria just mentioned, very old populations of stars. So about 6 months ago now, there was what's called a fast radio burst that was detected in one of these old stellar populations. So there's been a lot of these fast radio bursts observed. We haven't talked about these at all today, but they're very weird phenomena. They're basically short, very highly energetic bursts of radio emission that lasts, fractions of a second. Okay. And the source of these is not confirmed. We don't know exactly what it is, but there's a lot of hints that they originate from the very high magnetic fields associated with young neutron stars. So the fact that we observed one of these fast radio bursts in a very old population, where we know there aren't any young neutron stars that were formed recently from massive star evolution, because those all formed 10 billion years ago. So this means that there must be some way to form young neutron stars in old populations. So Ilaria mentioned this accretion-induced collapse phenomenon, where you maybe take a massive white dwarf and add a little more mass and make it collapse to a neutron star. This is maybe one way to do this, but this is all very not well understood yet. And the detection of this fast radio burst in this population sort of set myself and a lot of other theorists scrambling to try to cook up ways that you might be able to explain this observation.
Cool. Margaret, any takers, any weird and wild ideas?
I feel like I'm honestly drawing a bit of a blank on like really weird and wild things I've read in the past year. I think in terms of like knocking my socks off, I feel like one of the most exciting things that happened in the last year was like the launch of James Webb. And I think that was something that, I don't know, I think was really cool for me. Like I woke up at like 4 a.m. to watch the launch on Christmas Day. And I feel like, I use a lot of space telescopes in my research. NewStar, which I used, was only launched in like 2012. But I wasn't like working kind of like in the very specific like niche where I would have like really focused on it when it launched. And so I think it was just really exciting to kind of see one of these great observatories kind of going up. And I think it's just going to be so exciting to see all the stuff that comes out of it. And we've been waiting for a long time for it to launch in the astronomy community. So it was really exciting.
Yeah, yeah, I'm super excited to see some of the results that come out of it very soon. So, okay, well, that brings us to 9 o'clock. Thank you, Margaret. Wonderful presentation. Excellent responses to all the various hard-hitting questions, hard-hitting journalism from our audience. They pulled no punches and gave us some really doozies, especially that quantum gravity. We'll save that one for Saul. Thank you to our other panelists, Kyle and Ilaria. Excellent, excellent job explaining things. I definitely learned things today too, so I'm very excited about that. I didn't know you could have a smooth transition from a white dwarf to a neutron star with a little bit of accretion. I thought it was, you add that stuff, you go over the Chandrasekhar mass and kaboom. So I'm glad to have been here to learn some things.
Nice, you know, we still don't know. We don't know for sure, but yeah, it's a possibility.
Interesting. And then thank you to our audience for joining us. You took your Friday night and joined us to learn a little bit more about space and science. So so kudos to that. Thank you for joining us. A quick reminder that our next event will be Astronomy on Tap Los Angeles on Monday, March 14th, a week from this coming Monday. And the two topics that will be discussed are one of the NASA missions that's coming up to go to our nearest neighbor, Venus, called Da Vinci Plus. We have one of the staff scientists from the Jet Propulsion Laboratory who's going to be joining us and talking about that mission that she works on. The other talk will be on using using ways of measuring time from astronomical sources that proves and predicts different astronomical phenomena like gravitational waves and pulsar timing arrays, variable stars that reveals the distance scale to different objects in the universe, and so on and so forth. So it should be very interesting. And then finally, we will have an additional stargazing lecture like this one in a month on April 8th, Friday, April 8th, given by Professor Saul Tukolsky, who's an expert on numerical relativity, gravitational waves, black holes, and just gravity in general, which sounds kind of weird, but he's legit. So I encourage you to come back for those events as well. And I guess that's it for tonight. So thank you all for joining us, and we'll catch you